Question 7. Sulfur trioxide decomposes on heating to form an equilibrium mixture containing sulfur dioxide and oxygen. A sample of sulfur trioxide was heated and allowed to reach equilibrium at a given temperature. The equilibrium mixture contains 6.08 grams of sulfur dioxide. This is the sulfur dioxide here. 6.08 grams. I know its formula is SO2, so I can work out its MR. I've got a mass, I've got an MR. I can calculate number of moles. Moles is mass divided by MR. 6.08 is my number of grams. MR is a 32.1 for a sulfur. 2/16 for an oxygen is 64.1, 0.949 moles of this. But every time 2 moles of sulfur dioxide is made, only 1 mole of oxygen, half the amount of oxygen is made. So the number of moles of oxygen made is half of that, 0.949 divided by 2, 0.0474 moles of oxygen. It's asking me to calculate mass. Well, I know the MR of oxygen, 2/16 is 32, so 0.474 moles of oxygen equals the mass divided by the MR, 32. Multiply the two numbers together, 1.52 to 3 significant figures. There is no chosen 3 significant figures. It's because the number of grams is to 3 significant figures. 7.2. This is for an equilibrium mixture. When you get an equilibrium mixture containing gases, you've got to use something called Kp. Normally Kc is the equilibrium constant, where C stands for concentrations, but this time we've got Kp. And Kp is the partial pressures. I'll explain what those mean in a little while. So first of all, what you need to do is you need to have a look at the amounts of the moles and work out something called the mole fraction. So you add up the total number of moles of all of the gases. 0.32 add 1.2 add 0.6 is 2.12. That's the number of moles of all of them. And then you work out the fraction of sulfur trioxide that's in the mixture. So that's 0.320 moles of sulfur trioxide out of a total of 2.12, and that's something called the mole fraction. 0.32 divided by 2.12, which is the total number of moles, 0.15. SO2, 1.2 divided by the total, 1.2 divided by 2.12, 0.57, and O2 is 0.6 divided by 2.12, 0.28. Okay, now my Kp, it's calculated in the same way as a Kc. A Kc would be the concentration of SO2 squared multiplied by the concentration of O2 divided by the concentration of SO3 squared. And you do it in exactly the same way, except that Kp is something called the partial pressure of the SO2. So instead of the concentration, it's something called the partial pressure. Still SO2 squared, partial pressure of O2 divided by partial pressure of SO3 squared. So instead of concentrations, you've got partial pressures of things, and we use round brackets rather than square brackets. Partial pressure of SO2 squared multiplied by the partial pressure of O2 to the power 1, because there's 1 in front of it, divided by the partial pressure of SO3. How do I convert mole fractions into partial pressures? I take the mole fraction and multiply by the total pressure to work out the partial pressure. So if I had the total pressure, I'd multiply each of these by the total pressure, work out the partial pressure, plug them in, and work out Kp. However, this question is tricky because it's back to front. I've been given the Kp and it wants me to work out the total pressure. So this is what I have to do. To turn this into a partial pressure, I would take 0.15 and multiply by the total pressure. Let's call the total pressure P. So the partial pressure will be the mole fraction multiplied by the total pressure P. 0.15 multiplied by P. 0.57 is the partial pressure of SO2 multiplied by the total pressure P. 0.28 multiplied by the total pressure P for the partial pressure of O2. And I've been given the Kp. So Kp is 6.72 times 10 to the power 5. So this value here, which is the partial pressure of SO2 squared, which is 0.57p squared, 0.57p squared, multiplied by the partial pressure of O2, which is 0.28p to the power 1, because it's just to the power 1, divided by the partial pressure of SO3, which is 0.15p, and it's a squared because there's a 2 in front of it, so it's divided by partial pressure of SO2 squared divided by 0.15 squared p squared. Now I've expanded them, so 0.57 p squared, I've expanded it, expanded the this whole thing squared. 0.15 p squared in total is the same as 0.15 squared p squared when you expand it. So I've expanded these, and then what I've done is I've divided by p squared top, divided by p squared bottom, and it leaves me 0.57 squared, which is 0.325. P squared and p squared top and bottom have disappeared. 0.28p divided by 0.15 squared, which is 0.225. And then I've rearranged this equation. 7.62 times 10 to the power 5 multiplied by 0.0225 equals 0.325 times 0.28p, divided then by 0.325 and divided by 0.28, and it comes out that the total pressure was 1.88 times 10 to the power of 5, and it's in pascals because the kp is in units of Pascal. 7.3, for this reaction at 1050 K, that's the temperature, the equilibrium constant is 7.62 times 10 to the power 5 Pascal. At a lower temperature, 500 K, the Kp is 3.94 times 10 to the power of 4. So it's a lower pressure, lower Kp rather. So at a higher temperature, it's a higher Kp. Let's just have a look here. What's the Kp? The Kp is the pressures, partial pressures of these two gases on the right divided by the partial pressure of the gases on the left. So if it's a big Kp, it means that the partial pressures of the products, the things on the right, are high. So at a big Kp, which is this one, at a high temperature, there's a big Kp. At a high temperature, where there's a big Kp, there's a lot of products, a lot of the substances on the right hand side. So at a high temperature, I'm getting lots of substances on the right hand side. Explain how this information can be used to deduce that the forward reaction is endothermic. Well, if the forward reaction were endothermic, in other words taking in heat, if I provide heat, then it will go to the right hand side, because going to the right hand side it's endothermic, taking in heat. By Le Chatelier's principle, it says that whatever I do, it will lower or oppose that change. So it's going to the right hand side, it's endothermic, taking in heat. If I provide heat, it will go to the right hand side to try and take away some of that heat. So that's proving, therefore, at the higher temperature there are more products, it's moving to the right hand side at the higher temperature, and it must be endothermic because Le Chatelier's principle says if I raise the temperature and make the temperature high by Le Chatelier's principle, it will go therefore to the right hand side and lower that temperature because it's endothermic. The easiest way of saying that is Kp is higher at higher temperature. High Kp means the equilibrium would shift to the right to try and lower the temperature by Le Chatelier's principle. Use data from question 7.3 to calculate the value of Kp at 500 K for the equilibrium represented by this equation. Well, first of all, we know from the previous equation, from the previous question, that Kp is this. Kp is partial pressure of SO2 squared multiplied by partial pressure of O2 divided by the partial pressure of SO3 squared. So I know that. That's just written out again there. For this one, the Kp is the partial pressure of SO2 to the power 1 multiplied by the partial pressure of O2 to the half, because it's got half in front of it, divided by the partial pressure of SO3. So I am going to square everything in this. So Kp squared multiplied by partial pressure of SO2 squared, partial pressure of O2 to the half squared is just partial pressure of O2, partial pressure of SO3. So if I square everything here, partial pressure of SO2 becomes SO2 squared, the same as above. Partial pressure to the half squared becomes partial pressure O2. Partial pressure SO3 squared becomes this. So if I square everything here, it becomes this above it. So Kp squared, my new Kp squared, equals this, which equals 3.94 times 10 to the power 4. So Kp squared is 3.94 times 10 to the power 4. Kp therefore is the square root of that, which is 198.5. Calculate the units of Kp. Well, partial pressure is measured in pascals, so I've got partial pressure here. Partial pressure is just pascals. Partial pressure to the half is pascal to the half divided by partial pressure, so 3 is pascal. Pascal top and bottom cancel. Kp is pascal to the half, or pascal to 0.5, whichever you prefer.